Okay, so much like the direct comparison tests that I explained in the previous video, the limit comparison test uh, asks us to compare a series whose behavior we don't know to a series whose behavior we do know. But this one's easier to apply. So let me explain the test first, and then we'll definitely for this one do several examples. If possible, right, you may never have to apply the direct comparison test and can always depend on the limit comparison test. So let's suppose we still are dealing with series with non-negative terms. So let's suppose that the terms of one series are non-negative and the terms of another series are non-negative. And so we are thinking here that the series a sub n has unknown behavior, and we do know the behavior of b sub n, known behavior. And so let's think about the different scenarios we might have. One, what we do is we form the limit, we take the limit as n approaches infinity of the ratio of the terms are unknown, the nth term of the unknown series to the nth term of the known series. And if this limit gives us a finite numerical value that's positive, then the two series behave in the same way. So they will either both converge or both diverge. So let's think about why. If you think about this ratio, right? If that might have like powers of n in the top and powers of n in the bottom. If we get a numerical value, that means that the dominant terms of the nth terms have the same power. And so if they have the same power, we can say, well, they're kind of growing at the same rate. If they're growing at the same rate, then as we take the limit, if we'll get a numerical value, so they'll either both converge or both diverge. This will, I think, come clear when we do some examples. So the second scenario is that limit, so we're always taking the limit as n approaches infinity of the nth term of the series whose behavior we don't know over the nth term of the series whose behavior we do know. If this limit is 0 and we know that b sub n converges, then a sub n, the series, will also converge. And let's think about this a little bit. If in the limit this ratio is approaching 0, that means that these terms are growing at a faster pace than a sub n. b sub n is growing at a faster pace than a sub n. So if b sub n converges, since it's growing at a faster rate, a sub n must also converge. And the third scenario is if this limit is infinite. And that's going to mean that the series at the top, the terms will grow faster than the terms of the series at the bottom. So if we know that the bottom series diverges, and we know that a sub n's grow faster, then the series that we don't know, a sub n, will also diverge. And again, this has to do with rate of change, right? Rate at which these series are growing. If this is infinite, that means this guy is growing at a faster rate than b sub n. But if b sub n diverges, then that one, which is growing faster, must also diverge. Okay. Let's think about some examples where we might be able to apply this test. So we'll look at our first example. And again, we're going to have to choose a series to compare our unknown series to. So our first example is going to be the series. So let me write example here. from n equals 1 to infinity of n minus 5 over n squared plus 1. Good series to compare things to are the p-series or the geometric series. How do we think about what we compare to? Well, I always try to attend to the dominant terms and reduce that. So here I see an n over n squared. That's going to reduce to 1 over n. So we're going to compare our series to the divergent harmonic series. And let's see what happens. So this one takes a little more work, but it's pretty straightforward. We're going to take the limit as n approaches infinity. In the numerator, we're going to put in the nth term of our unknown series. Well, we know it, we just don't know its behavior. And I'm going to divide that by 1 over n, the harmonic. Now, dividing by a fraction is the same as multiplying by the reciprocal. So we'll have n minus 5 over n squared plus 1 times n over 1. Now, if you look at the powers at the top, if we were to multiply this out, that's an n squared, bottom n squared. N squared over n squared is 1. So in the limit, this will be 1 because the powers are the same. So this is going to go to the ratio of the coefficients. So we have a case like number 1 in our series. Because we're getting a finite value, the two series behave in the same way. So our given series will also diverge because the harmonic series diverges. So we would write this diverges. We use the limit comparison test with a harmonic series comparison with a divergent harmonic series. And so since we got a numerical value, they both behave the same way. Okay, so let's try another example of how to apply this. So let's look at the sum from n equals 1 to infinity. So we use this test usually when we have rational expressions as our nth term. So here we have n cubed minus 2 over 4n to the 5th minus n cubed minus 2. So again, I'm going to attend to the ratio of the dominant terms, and that gives me an idea of what to compare our series to. So I'm going to compare this one to the sum from n equals 1 to infinity, n cubed over n to the 5th. That's all I care about. That's 1 over n squared. This is a p-series, and since p is greater than 1, we know this is a convergent p-series. So now we're going to set up the limit for the limit comparison test. So we'll do limit as n approaches infinity. Our series, n cubed minus 2 over 4n to the 5th minus n cubed minus 2. All of this is divided by 1 over n squared. So we'll multiply by the reciprocal, just like we did in the previous example. So we have n cubed minus 2 over 4n to the 5th minus n cubed minus 2. We're multiplying by n squared over 1. In the top, we have an n to the 5th power with a coefficient of 1. In the bottom, we have a 4n to the 5th power with a coefficient of 4. So in the limit, this is going to go to 1 over 4. That is a finite number, numerical value. That's like case 1 in our limit comparison test. So we can say that our series also converges. These will behave the same way. It converges because we used the limit comparison test with a convergent p-series. So with convergent p-series, right? So we have to explain what test are we using, what are we comparing to? This was a convergent p-series with p equal to 2, greater than 1, that's why it converges. All right, let's try another example. This one, let's look at the sum from n equals 1 to infinity of 1 over 2 to the n minus 1. 2 to the n minus Okay, so I'm thinking, all right, what do I compare this to? Well, let's think about what's dominant again. Dominant here is going to be this series, 1 over 2 to the n. Do we know that behavior? It's not a p-series, but it is a geometric series. So if you think about this series, this can be written as 1/2 to the nth power. That's geometric. When the base is fixed, that's geometric. And geometric series converge as long as the common ratio r is between -1 and 1. Sometimes we can write that absolute value of r is less than 1. Well, here our common ratio is 1/2. That's less than 1. So we're dealing with a convergent geometric. So let's run our limit comparison test with the convergent geometric series. So I'm going to take the limit as n approaches infinity, 1 over 2 to the n minus 1. I'm going to form the ratio with the series whose behavior we know. Again, like I've done in the other examples, we're going to multiply by the reciprocal. So we have 1 over 2 to the n minus 1 times 2 to the n. And so this is the limit as n approaches infinity of 2 to the n in the numerator over 2 to the n minus 1. All right, I think this is going to go to 1, but I'm going to try to prove it more formally. I'm going to divide numerator and denominator by 2 to the n. Over 2 to the n, which is itself, right? I can divide anything by 1 anytime we want. So this is going to give us the limit as n approaches infinity, 2 to the n divided by 2 to the n in the numerator is 1. In the denominator, this 2 to the n divided by that is 1 minus 1 over 2 to the n. This is a little bit clearer about how this limit behaves. As n gets really big, this term's going to go to 0, and this just gives me a 1. Remember, with the limit comparison test, if we get a numerical value, then both series will behave the same way. So therefore, our series converges. I'm not going to write the series, and this is converges. We did a limit comparison test with a convergent geometric series. And let's see, I have more examples, but I think I'll wait to do a little questionnaire with you and talk through some problems together. So we'll leave it here. Important parts here with this limit comparison. First of all, you never really have to use the direct comparison test if you don't want to. You can always use the limit comparison test. It is easier to apply. We compare series to geometric or p-series. Those are two great series to compare unknown series to. And so what we're usually looking for is a rational function, or that the nth term is a rational expression. So one polynomial divided by another. Okay, in the next video we'll do some problems together, and then we'll work on the ratio test.